Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome to session 4 of the theoretical discussion on remote sensing applications in engineering geology. So, in this lesson we are going to just cover the principles, essential principles of different procedures of remote sensing that are normally used in different applications, particularly geologic mapping that we considered in the last session. Okay. But before we proceed with the discussion subject matter of this particular lesson, we are going to discuss the questions that I asked in the previous presentation. The first question that I asked was, what is meant by the term outcrop? Outcrop is essentially it essentially is a body of bedrock that is exposed at ground surface. Then the second question that I asked was that what are the different types of contacts between geologic units. We discussed this one in great detail in one of the previous presentations, and the types of contacts that we considered in that at that time were conformal contact, non-conformal contact, and one of the types of conformal contacts was we discussed a type of contact called gradational contact. So, these are the three different types of contacts we discussed earlier. Now, contacts can also be classified depending on whether the contact is through the plane of a fault or not. So, the contact could also be classified as a fault contact or depositional contact, depending on whether or not contacts between two different geologic units is across the plane of a fault or through a surface of deposition. The third question that I asked was, how would a sandstone layer appear on a geologic map of a deep river canyon if the layer dips at 75° in the downriver direction. Now, recall from what we discussed in the previous presentation, classroom presentation, was that when there is a dipping layer going across a valley, then the outcrop of that particular layer takes the shape of a V or an U. So, this is the outcrop of the layer seen on the plan view. That means, when we are looking at this particular map upside down from an elevation looking down. Now, this is the outcrop of the geologic unit that we are looking at. Now, in this case though, and the reason why the outcrop actually takes a shape of an U or a V inside the valley is because near the valley bottom at the point where the outcrop is at the lowest level, lowest elevation, that is going to proceed in the down dip direction. So, at this location the outcrop elevation is the lowest compared to the elevation of the outcrop at the flanks of the V shape. That is the reason why the tip of the V always points towards the down dip direction, irrespective of the surface topography within the valley. So, the valley could either slope in this direction, or this is the valley, this could be the valley slope, or the valley slope could be the other way around. Irrespective of the direction in which the valley slopes, the down dip is going to point, the down dip direction is going to be pointing towards the sharp corner of the V if you have got a dipping layer crossing a particular valley. So, in this case though, the dip angle is quite near vertical. So, you may not get a pronounced V shape as shown on that particular figure, but what you might get is a shape like this. So, this is the valley or canyon that we are considering, or canyon, and the shape of the outcrop may look somewhat like this. And again this is going to be the direction of dip of that particular layer. So, that takes care of all the problems that I asked in the previous presentation. So, with that said, I am going to proceed with the subject matter of this lesson. So, what we are going to discuss here, we are going to discuss essential principles of engineering of remote sensing applications in engineering geology. We are going to consider the procedural details, essential details of the procedures of several different types of remote sensing, like aerial photogrammetry, LiDAR, and IFSAR we are going to discuss in this lesson, and we are going to try to develop a notion of how to use these remote sensing procedures in simple problems of geologic mapping. Okay. Now, preliminary concepts of engineering, we begin with the preliminary concepts of engineering of remote sensing application in engineering geology. We first of all need to understand what we mean by remote sensing. Remote sensing essentially means deriving information about the characteristics of a geologic deposit without any physical contact with the deposit. For example, if we take a photograph of a particular geologic deposit and derive some of the characteristics of the deposit that are of interest from engineering standpoint, then that kind of investigation is going to be known as remote sensing. Then remote sensing, the principally remote sensing relies on the reflectance characteristics of different surface materials over various portions of the electromagnetic spectrum. Now, typically not only visible light is considered, but infrared, near and far infrared are utilized in trying to get the reflectance characteristics of different materials. We are going to see how different materials behave in these different regions of electromagnetic spectrum. Microwave is also used in remote sensing. Thirdly, we typically require multispectral coverage to derive useful information about different geologic units. Then remote sensing procedures that we are going to consider in this lesson may or may not may or may not use its own energy, and depending on whether or not it uses its own energy, the remote sensing procedure is classified as active or passive. With the active remote sensing procedures are essentially they require their own energy source, whereas passive remote sensing procedures require no energy source. They purely depend on the reflected electromagnetic waves that bounce off of those of different geologic units. The origin those electromagnetic waves might originate from sources other than the source specifically dedicated for the remote sensing investigation. Now, let us understand why we require multispectral image. In other words, why information derived from a particular wave band is not going to be sufficient in the normal investigation procedure. What we are going to consider here is the reflectance characteristics of sand and clay, and we are going to consider that there are different moisture contents within these deposits. So, in the vertical scale we are plotting the percent reflectance, reflected, and in the horizontal scale we are plotting the wavelength in micrometer. Now, typically, and let's draw the scale as well. So, we are plotting in the vertical scale, we are plotting from 0 to 100%, and in the horizontal scale we are plotting from 0.5 micrometer to say 2.5 micrometer. Typically, the reflectance characteristics of sand, dry sand, is going to take a shape like this. This value where it saturates is approximately 60 to 70%. On the other hand, if you look at clay, clays are much less reflective than sand, and typically what you might get is a shape like that. So, this one is sand and the lower one is clay. Now, this one is dry sand, by the way. This one is dry sand and this one is clay with little moisture content. So, it is moist clay with moisture content of say 5%. Moisture content is typically defined as the volume of water to the volume of dry soil, is the ratio of volume of water within a soil matrix to the volume of dry soil. Now, let us see what happens when we try to saturate the sand that was originally dry. So, when we saturate the sand, then what happens? The sand may actually come down to have a reflectance characteristics sort of look like this. Now, you see these valleys are going to occur, are expected to occur at 1.4 micrometer and 2.7 micrometer, actually 1.9 micrometer, sorry, 1.9 micrometer. We are not plotting 2.7. So, this one is 1.9 micrometer. These values are indicative of presence of water. They are actually absorption they are absorption bands of water, and they confirm the presence of water within the soil skeleton. Now, look at the similarity of the moist clay and saturated sand with a moisture content of say about 8% moisture content. This one is moist sand. So, what I want you to look at is the remarkable similarity of the moist sand and moist clay over in this region of bandwidth from about 1.5 micrometer to about say 1.2 micrometer. So, they are largely similar. Now, if we do not consider the absorption the reflectance characteristics beyond 1.2 micrometer, greater than 1.2 micrometer, we will not be able to distinguish whether we are looking at moist clay or moist sand for in most cases. Now, this kind of you can realize the importance then of covering a large range of wave bands of wavelengths in the remote sensing technique in order to distinguish between different types of geologic materials. Okay. Getting back, next we are going to talk about the reflectance. Let's explore what are the factors that the reflectance generally are influenced by. So, you understand that reflectance depends on the geologic characteristics of the material that we are trying to identify. Then it also depends on other things like what are the other constituents that might exist within that particular geologic body, geologic material. For instance, the example that we just considered, in that we had water as the other constituent that was present within the body of sand and the body of clay. Now, you could also imagine that there could be other types of chemicals present in a geologic material. For instance, there could be iron oxide that might be present within a surface soil layer, and depending on whether or not iron oxide is present, the reflectance signature is going to be quite different. And you can expect that many of you might know that the color of iron oxide is red. So, the reflectance characteristics of a material, of a geologic material containing iron oxide is going to be much richer in the red wave bands compared to another material of very similar characteristics, but without iron oxide. Then the reflectance characteristics also is going to be affected by the organic content, the density of vegetation and type of vegetation that might grow on that particular geologic unit, what is the wavelength of radiation which is considered in the reflectance signature. And again we want to state, as I explained in the previous sketch that I was drawing, that we need to consider a wide range of wavelengths in order to distinguish different geologic materials, because of the non-uniqueness that are going to crop up because of different combinations of chemical constituents that might be present in a parent geologic body. Okay. Now, let us consider the type of or the range of wavelengths that are normally exploited in existing platforms of remote sensing satellites. this slide here actually shows the entire wave band of electromagnetic spectrum ranging from 10 to the power 12, 10 to the power minus 12 meter to 10 to the power 4 meter. Here what we got, we actually, as you all know, that we begin from gamma radiation at the shortest range of the wavelength, then we gradually transition from X rays to ultraviolet rays to the visible spectrum, then infrared, microwave, and eventually into radio waves. So, the spectrum that is normally exploited in remote sensing are the visible spectrum, the visible light, near infrared, to some of the remote sensing platform, they also utilize the far infrared, and there are quite a few satellites that exploit the microwave wave bands of the electromagnetic spectrum. Now, you know, from visible light we can distinguish different objects, like we can see whatever we can see out of a photograph, we can also distinguish when we take a photograph from a satellite platform in the visible wave band. Now, near infrared actually is the they are actually characteristics of different constituents within the geologic unit. Like for example, depending on what is the density of vegetation and whether there is any water body present, depending on those things, the reflectance characteristics in the near infrared are going to be different. We are going to discuss these things in greater detail in the next little bit. Now, far infrared is essentially that essentially indicates what is the amount of heat that is coming out of a particular geologic body, and this information is also useful in some remote sensing techniques. But most of the satellites that we are going to we normally use, they cover the visible light and the near infrared signals, and out of these satellites common are Indian remote sensing satellites, then Landsat, and the SPOT satellite of the European Space Agency. In the microwave band also there are useful information about geologic characteristics of materials, and there is a satellite operated by Canadian Space Agency, it is called RadarSat, that generates useful information in the microwave wave band. In the radar, those are essentially radar imagery. Okay. Now, these platforms are essentially satellite platforms. They actually go around in space and circle around the earth every so often. We are going to look at the characteristics of these satellites later on. You could also think about similar multispectral imagery covering a large range of wave bands based on airborne systems other than satellites. Like for example, you could fly these remote sensing tools on aircrafts or even blimps, and they are also used in remote sensing techniques. Now, airborne imagery is going to give you a very high resolution pictures within these wave bands in comparison with the radar imagery, but the expense that is involved in carrying out a project specific airborne survey could be quite large and may not thus be possible to be undertaken in projects that are of comparatively smaller size. But in these projects, satellite images could be purchased from the remote sensing agencies that I indicated in the previous slide, and these satellite photographs also generate quite useful informations, but to a much larger scale. Okay. Now, this slide actually summarizes the different the characteristics of different airborne different satellites that are used for getting remote sensing images. At the top is the Landsat thematic mapper. You can see that the altitude of this particular satellite is about 705 kilometer. Then the bands that are obtained, I mean different the bands that are obtained, number of bands that are obtained from this platform is 7. The swath width of this satellite is 185 kilometers, and the spatial resolution of this satellite is 30 meters. So, in other words, in one coverage, this particular satellite is going to cover a width of 185 kilometer on the surface of the earth, and you could distinguish two objects only if they are separated from each other by about 30 meters. If you want to actually get a better resolution, then this particular satellite, the images obtained from this particular satellite may not be useful. But you look at Spot 4 satellite of the European Space Agency. Landsat is a satellite operated by NASA of the US. Spot 4 satellite, on the other hand, it has got an altitude of 830 kilometers, but it gives only photographs in only 4 wave bands. It has got a smaller swath radius of 60 kilometer, and it has got a much better spatial resolution, which allows you to distinguish two objects that are separated from each other only by 20 kilometers. You look at RadarSat, actually Indian remote sensing satellites, it has got a larger altitude. It operates at 900 kilometer above the earth surface, and it also covers 4 wave bands, but it has got a larger swath width than Spot 4 satellite. This one has got a swath width of 147 kilometers, and it has got a spatial resolution that is slightly poorer than the Landsat thematic mapper imagery. RadarSat, on the other hand, it has got actually you might remember that RadarSat obtains photograph in the microwave band. It has got a much better resolution, and you could distinguish two objects even if they are as close as 3 meter from each other. This one has got a swath width of less than 500 kilometer. Let me explain actually what I mean by the swath width, these different terminology that I used when I was talking about the satellites. Now, consider a satellite that is operating at some elevation above the earth, and this elevation depends on the platform that you are thinking of. For example, in case of IRS, this elevation is about 900 kilometers. So, this is the surface of the earth, this one is the surface of the earth, and by swath width what I mean is